Awesome. I think we're ready to go with our next one, which looks like it's going to include a live demo, this is going to be exciting. So Paul, you're not from, I don't actually want to. Paul works from ADI, and once again, ADI is one of the platinum sponsors of this conference. They have a talk tomorrow morning as well. So we're very, very thankful for everyone who made this conference possible. So with that, I'm going to hand it off to Paul to talk about IIO integration.
Hello everybody. I'm quite excited to be here. So I will present myself again. My name is Paul Cercueil. As you said, I work for the devices in Germany. As said, my English is not 100% perfect. I speak a little bit of French accent plus German accent. That's not a really good mix. Today I want to talk about some of the work that we've been doing at IIO devices around IIO, the IIO framework of the Linux kernel, and the integration with GnuRadio. Just a warning, so I'm a software developer at IIO devices, and maybe like the person in the room that knows less about radio. So what is exactly the, first of all, what is IIO? IIO stands for Industrial Input Output. That corresponds more or less to everything that is in some sense now to digital converter or digital to analog converter. That can be precision, ADC DAX, high speed ADC DAX, accelerometers, sensors, temperature, pressure, sensors, gyroscopes, IMUs, etc. For all those devices, the Linux kernel has a specific framework called IIO. All the human interfaces, devices are separate in the input framework. So all the non-human interface devices are in the IIO framework. So it's been in the Linux kernel since more or less 2009. It was integrated in the 2.6.32 kernel. And it's been out of staging, the staging area where all the new experimental stuff comes in the Linux kernel since 2012 in the 3.5 kernel. As of today, in Linux 4.3, we have more or less 220 drivers. Each driver can support more than one device. So for instance, only for ADI projects, we have more or less 70 drivers that cover 400 products from ADI. I won't really answer into the details of the IIO framework. I will just explain a bit what is the interface that the Linux kernel through this framework gives to the user specifications. So there is a configuration interface provided by the virtual file system called sysfs. The user space application, by reading special files, will be able to control the hardware. So for instance, here is a small list of a couple of files that you could find in this virtual file system. So for instance, those files correspond to one device which has the name IIO device 0 with two channels, one output channel, voltage 0, one output channel, voltage 1, and a couple of parameters, mode, scale, power down, etc. There is a second interface that may or may not be used by all drivers, which is the buffer interface. That's a special node in the Linux file system where you will be able to read and write the samples. It has there are two possible ways of actually writing the samples, either using the standard IO calls, F-read, F-write, etc., or only in the ADI, on the ADI Linux kernel. There is a faster way using advanced techniques like The problem with this kernel interface is that it's very simple, and by simple I don't mean that it's easy to use. I mean that it doesn't have a lot of advanced features. For instance, you can only have one application at a time using a device. The other problem is that every person that wants to write user-space application using IIO devices have to rewrite the same code again and again. So my first job when I joined another devices was to write a software library called GnuRadio that takes care of all the low-level details of the Linux kernel, and it allows you to write a user-space application that uses IIO devices much more easily than just playing with the kernel. So this is the URL at which you can actually get the library. It's LGPL version 2.1. It was written in C, but now it has lots of buildings for different other languages. So it has Python buildings, C# buildings, C++, and can be used under MATLAB and Cercueil. It's more or less 1 year old now. So in the library you have 4 main objects that you will manipulate. The IIO context object, which represents more or less one instance of the library. It will offer you 0 or more IIO device. Each IIO device object corresponds to one device reported by the user. Each device can have 0 or multiple channels. And the device channels can have attributes. And the attributes are what you actually read, write to change the parameters. And the IIO device can be associated with an IIO buffer, which is the object that can be used to read and write samples. So it's been designed from the very beginning with modularity in mind. And if you say that the application that you write that uses GnuRadio will only use the upper part of the library, which is composed by all the API functions and the object that you will manipulate. The library has lower level that can be interchanged. For now, we have a local backend and a network backend. I will talk about those later. And the plan is to have also USB and PCIe Express backend. The very important thing here is that when your application, if you write it to use GnuRadio, it will run independently of the backend used. So you can write an application made to work on the target board using GnuRadio, and it will work automatically over the network on your PC. So the local backend of the library is to be used when the application will run directly on the target board. So obviously it's only available for Linux because the IIO system is the framework of Linux. It has the same limitations as the kernel. You can't have multiple applications using the same device at the same time. As the system-face virtual file system and the device nodes are owned by the superuser, you need superuser rights to be able to run your application. The network backend will connect to a server that runs on the target. So it can actually run on much more operating systems than the local backend. It runs on Unix. So Linux, BSD, runs on OS X, it runs on Windows. It's more secure in the way that your application don't need to have super user rights to run. It is more flexible because the server that runs on the target board will handle things like concurrent access, so you can have two applications using one device at the same time. If one application asks for the samples for two channels and the second application asks for the samples for only one channel, the server will correctly dispatch the samples. So that's more or less how it looks. Laser pointer? No, okay. So you can have one application running, let's say GnuRadio, for instance, that runs on the target board, that we use libiio, that we use the functions, the API functions of libiio, and that can run either using the local backend or that can run on the network backend. So using the local backend, we can just use the IO devices reported by the kernel, or it can run over the network. So we have a couple of tools that helps us develop that. The IIO inform tool will give you a structure of all the devices, channels, attributes that are found by the Linux kernel, print the values. The IIO dev is useful when you want to make a capture of samples. And that's also IIO subsystem on libiio. So that was very software oriented, but that was a bit necessary to explain the radio blocks, because the GnuRadio blocks are just small wrappers around the library. They can be found at that repository header. The reason why IIO developed those blocks on the radio is that we actually have lots of customers that ask for GnuRadio for testing their RF equipment. It's not really meant for people who just want to design their Azure application where other solutions like the USFP, Cyclic could be much better. So the reason why we didn't work on the radio before was that it was just not possible. The fact is, on the target board that this and the Xenix from the Z-board from Xenix, the board has only a small dual-core ARM CPU that runs at like 800 megahertz. GnuRadio just can't run on that. We actually tried. The biggest program that we can make is a radio that runs at less than 1 megabyte per second. So the solution that we have now is that the target board will just act as a passive component and we pass the samples around to the PC where the GnuRadio runs. And for that, we developed a couple of blocks. The first ones are pretty generic. We just enter the parameters of first, for instance, the host name of the target board, the name of the device, the channels that you are interested in. Okay. Device that will be used, the IO device that will be used to read write samples, the IO device that will be used for configurations, the channels that you want to read write from. Yeah. Well, so I feel now something can go wrong if we go wrong. Yeah, so basically with those blocks you can use GnuRadio with every device supported by the IIO subsystem. That means you can use it with high-speed converters, you can use it with sensors. You just need to specify the correct device name and channels. So we also developed a couple of blocks that are specific to our hardware. Those ones are just wrappers again around the generic blocks, and they just pass the correct device name automatically, the channel names, and they offer a couple of more parameters. Those parameters are just appended to the array list of strings. So you can actually do everything that this block supports with generic block. A little bit about the performance that we get. So it depends on the target board. For instance, the Z board is very CPU limited. With the Z board we can get around 15 megacycles per second, and after that the server running on the Z board that just copies from the hardware to the network card. We hit 100% CPU just copying data. On different boards, we are limited by the network, and we can get around 18 megacycles per second for one IQ challenge. That corresponds more or less to 480 megabits per second, which is the maximum we can get on the network with the TCP connection. So we have ideas to improve that. The first one is to reduce the CPU usage on the target board using zero copy techniques. Zero copy is that that will be copy the data using DNA from the transmitter to the memory, and then directly using DNA to the memory, from the memory to the network. So there is no CPU, the CPU is not involved in the process. Other improvements are to develop other interfaces. So to add a USB 3 interface and PCIe interface as well. So that's the end of my presentation. I really am sorry about the demo that doesn't work. If you have I can try to get it to work. If you have questions in the meantime.
All right, we're going to have some mixed questions in hacking time. So does anybody in the audience have questions? Yes, Lee.
Are you able to have multiple IO device sources? So you have, say, distributed sensors?
Sorry, would you mind repeating the question to the mic? We want to make sure it all gets recorded.
Yeah, so if I understood correctly, you're asking if we can have multiple source blocks at the same time in one program. That's possible if you're using the network backend. So if you use the local backend, then you can only have one application using the device at the same time. But on this case, there is the server running on the target board, and we just enter the IP address, and that would work as if two clients will connect at the same time to the server, so they will get the same data from the server, so it would work.
All right, any further questions? No? Okay. Let's thank our speaker. Thank you so much, Paul.